Hello. In today's class, we will continue our discussion on geothermal energy. In particular, today we will look at some aspects associated with the technology part of the process. We understand that inside the earth there is a lot of heat and we are trying to extract it. So, a little bit more on the technological side of it, some aspects associated with some challenges associated with the technological side of it is what we will try to focus our attention on. So, in this context our learning objectives for today's class are basically to describe the different conditions relevant to geothermal energy availability. Okay. So, it is not available in the same kind of quality or quantity, I mean quantity is not the issue, quality at different locations. So, if you actually go about trying to find it, you may find it with different levels of heat that is available there, temperature that is available there, even what is available there that is coming out maybe naturally from under the ground. So, these are things that we have to look at. Then we would also like to understand that in this context, since what is available underground may be different at different locations, what are the variations in geothermal plant design. Okay. So, what are the typical kinds of variations that people have in relation to geothermal plant design. So, I think these are the two major ideas that we would like to focus our thoughts on and go through related information. We saw this in the last class, that we basically saw that as you go deeper and deeper into the earth, the temperature goes up, and that is basically the idea of this whole geothermal energy process. I also told you that these are all based on models. The actual temperatures that you see here are all based on models, and so you can see variation from model to model. So, these are not hard and fast temperatures, these are sort of estimates based on different models, and as of now we have no real way of actually measuring these. In fact, even though the core is only 6,400 kilometers below us, you can actually learn a lot about planets that are far away from us, stars that are far away from us much more effectively than you can learn about the core that is just directly below us, because we cannot access it, whereas you can actually use astronomical instruments to access all of those. Incidentally, even though the temperature is going up, one of the points that you must find interesting perhaps to note is that the inner core, which is where you are seeing the highest of the temperatures, even though this may or may not be the exact number that we need to look at, the temperature is so high there that in principle at about if you cross 5000 degrees C and you go if that kind of a temperature you cross, essentially all metals will be in liquid state. You are not really going to have any solid metal at that point, but if you actually go to the core, the estimates indicate that in the core you actually have solid metal, you do not have liquid metal, and the reason is simply that whatever you see as the melting point, which you see in the data that you see when you go and look up melting point of iron or melting point of copper or melting point of aluminum, whatever the temperature that you see there is the temperature which is the melting point of that metal at atmospheric pressure. Okay. So, melting point, T melting point that you typically see assumes that it is at atmospheric pressure. So, that is equal to at 1 atmosphere, and as you can as we sort of saw, you could have several million atmospheres if you go down based on how much of pressure is being collected there. So, therefore, the pressure is very high there, and under those conditions, even though you are well past the melting point, the metal is forced to stay solid. The atoms are pushed close enough that they stay in their solid state, they do not break free and float away as liquid. Okay. So, therefore, inner core is considered to be a solid material, and in fact based on all the estimates, based on the fact that the earth has magnetic properties, various other the density of the earth, various other things, the expectation is that these are the kinds of compositions for the center of the earth. Incidentally, along similar lines, because of all this heat and pressure that is there, potentially this is something that you could this is a form of energy that you could extract in other locations too, in other planets too, if a similar situation were to exist. Of course, that would require some kind of a crust and then some hot material beneath it. So, some places that may not be the case. So, if you have a gassy planet, then that is not the case, then there may be no well defined surface on which this can be done. But this is an idea that is of interest even for space exploration, because at various planets, depending on where you are, you could get energy directly from within the planet, as opposed to say solar energy, etc. This may be relevant based on where the planet is located. This is just an interesting aside, and in all those cases again based on the pressure, the central part may be solid, the central inner core may be solid. Okay. So, for example, theory suggests that if you look at the center of say Saturn or center of Jupiter, the temperature and pressure and composition are all just right, that at the center of those planets it is very likely that you have a big diamond. Okay. So, so you know we look for diamonds and it is such a scarce item here on the planet, on our planet, and it is so expensive. You may have a diamond sitting in the center of Saturn or Jupiter which is larger than our planet. So, that is possible, we do not know that that is true, but the conditions are right, the high temperature, the high pressure and the amount of carbon that is present create circumstances that are very similar to what is required to create diamonds. So, this is just something that is of interest. So, different planets have different circumstances, but many of them have there is a chance that several of them have some energy in them. Certainly on Earth we have this energy that we are trying to tap. Okay. So, one of the big activities associated with locating and tapping of geothermal energy is this idea of prospecting. Okay. So, prospecting is simply exploring to find out what is available where, that is essentially what it is. So, people do prospecting for all kinds of different things. I mean, they may be prospecting for a particular ore, they may be prospecting for gold, they may be prospecting for diamonds, etc. So, even for geothermal energy, that is basically the idea. There are people who study the geology of various locations of our planet, and then so they try to understand what are better locations for the plant. As we discussed, potentially you could dig a hole at any place, and based on the kind of temperature you get at some depth, you can actually run a geothermal plant. So, in some sense the location is not totally critical. You can actually do this at multiple locations, and it is not impossible to do it that way, but there are better there are locations that are considered better locations, and to identify those locations you have to do prospecting. So, a considerable amount of time is spent to locate various regions that people think might be of interest, maybe because there is some hot water already coming out from under the ground, which suggests that there is some hot spot below, where you are able to access the heat at maybe a much shallower depth, you are able to access higher heat at a shallower depth. So, therefore, there may be better locations, and therefore, there is interest to explore those locations and see what you can obtain at those locations. So, to do that, actually what they do is they try to make a chart of some sort where you have a map, and then at in the map at various locations you indicate what is the temperature at various depths. So, therefore, you will get some kind of an isothermal line, you will find out that at which depth you get the same temperature at various places. So, if you are getting higher temperatures at lower depth, then potentially there is a some hotter region below. So, that may be a region that is more interesting for us to explore from the perspective of geothermal energy. So, for example, in India, a place where they are trying to really set this up, they have done this kind of geological exploration in several places in India. So, there is this Balrampur district in Chhattisgarh, a particular place called Tatapani in Balrampur district, Chhattisgarh, which is where they are doing putting in an effort to set up a geothermal plant. And so, that is where we are likely to see some activity come up from the Indian perspective. But all of that again, as I said, relates to this initial step of prospecting. So, it also, the prospecting also does multiple other things. I mean, so it is not just locating the region which is of interest. To understand what is that region, they also drill cores, I mean drill through that location, and pick up what kind of material is located at various locations in that region as you go down in depth. So, it is a temperature, so they are locating finding out temperature as a function of depth. And composition as a function of depth. So, composition means not necessarily chemical composition, we are looking at what kind of rocks are there, what kind of, I mean, is it sandy, is it full of rocks, and if so what is the thickness of the rock layer, how much of sandy area you have to go through, what kind of clay is there in that region, what kind of soil is there, how deep it goes. So, those kinds of information. This is very, this may not seem immediately relevant, but it is actually very useful in identifying low density regions. So, even within the same area, so supposing you have located a particular region where it seems like there is some hot spot below, even in that region you can check out multiple neighboring locations to see if there is one region where the drilling seems to be going much more easily, right. So, that enables the setting up of the plant in a much more easy manner, and therefore, this is a very important initial activity. And incidentally, I mean this is done so extensively in order to locate these plants, nearly 40% of the cost of geothermal energy is associated with this exploration process. So, and that is because they set up a sort of small scale plants are set up, small scale drilling is done. So, small scale drilling is done, small scale meaning the plant is actually almost like a mock plant they will set up, they will actually have to drill a hole into the ground to some reasonable depth to understand everything, to understand the temperature as a function of depth, to understand what geological features are there as a function of depth. You can also see if there has been some relatively recent melting and solidifying in those regions, that gives you an idea if that has been a relatively active location, so to speak, and then get this information together. So, you have to drill these holes and these are being done at various locations, and each of them costs a fair bit of money. So, nearly 40% of the cost of geothermal energy is associated with exploration. So, a lot of work is done on this remote sensing to get a better sense of what features are available at larger area of land, so that they can identify these locations much better. Therefore, in fact, the general thinking in the field of geothermal energy is that it is much more important to invest in technologies that help you in this exploration process, that will help you do this exploration much more effectively, much more efficiently, in a much more time bound manner, so that you can get all this information without a whole lot of delay and without a whole lot of expenditure of money and resources. So, if you can cut this down, if you can cut down this exploration cost significantly, the cost of the plant itself comes down, because this exploration cost is all getting tied into the plant. Eventually, when the plant comes, you have to recover this exploration cost from whatever it is that the plant produces, and if you take that into account, 40% is very high. 40% of the cost being the exploration is very high, and that is mainly because you have to actually make those drilling holes at various locations. It is not something that you cannot easily just get this information by taking photographs, etc. You have to drill, and that is the reason why this seems to be expensive. So, but prospecting is a very important activity in this context. Incidentally, so plants have been set up around the world in this context, and as I said, in India, in Chhattisgarh, they are working on setting one of these up. The largest such plant is in California. It is about 1500 megawatt plant, has multiple, I think multiple drills are there at that location, and you have about 1500 megawatts being generated there. Number of other countries have been involved in this process. You can see here in Philippines, if you take the 10 largest plants that are around internationally, then you have 3 of them being in the Philippines. So, that it seems to be quite an important form of energy capture that is being pursued actively. So, in Philippines we have 3 of them. In the US and in Indonesia there are 2 each. 2 of these large plants are there, including this one in California, and in Mexico, Italy and Iceland you have 1 each. So, clearly this is a worldwide phenomenon, lot of nations are looking at it. We have not actively pursued it to the extent that these plants are already set up and generating electricity and so on, but we are also considering looking at it, and we are in the process of setting up a plant. So, The again the nice driving force for this is that I mean you do not really need any there is no pollution coming out of it, it is kind of a clean form of energy and potentially infinitely renewable. I mean it is going to last for such a long time that you do not have to worry about it running out of it, so to speak. So, this is the sort of the global scenario in this context. Now, let us say we have done some prospecting. Okay, so, you have done some prospecting and you locate a particular region where there is very high temperature, and in fact, when once you drill you find actually there is a lot of hot material coming out from there, typically steam. So, that is what is coming out. So, based on the location and the temperature, essentially based on the temperature, you have multiple possibilities of what you can get from that location, right. So, either you can get because if the temperature is pretty high, then you may end up getting what is called superheated steam. Okay. So, water boils off and then you get steam, and at that point as it just about boils off and you just about create steam, that is called saturated steam. So, that can condense relatively easily because you are just past the boiling point. If you heat it distinctly above that boiling point, that steam is heated distinctly above the boiling point, then it is called superheated steam. Okay. So, superheated steam is that steam at a temperature distinctly above the boiling point. Okay. So, that is superheated steam. Right. So, typically superheated steam, so the advantage of superheated steam is it is not going to immediately condense and generate water. Okay. So, this is may not seem like much, but we will discuss that in a moment to understand what is the big significance of it if we say it is not going to condense all of a sudden, so to speak. First of all, in the grand scheme of the find that people have as they go about prospecting, this is relatively rare to find. Relatively it is there in some locations, but it is relatively rare to find superheated steams directly coming out from underground. But if you do find it in a location, it is a big positive because that means you can directly start putting a plant there and start operating it, and you can directly use it to run a turbine. Okay. So, you can run a turbine directly using it. We will just see some schematics of this in just a moment, but basically the steam can be taken to run the turbine. The one issue that you have to be cautious about is that even in thermal power plants, they are creating superheated steam and then sending it in to run a turbine. So, that in that sense conceptually once the steam is generated, the process is the same, you send it to run a turbine. Now, the only difference between say a thermal power plant situation and this geothermal situation is the fact that when you do this superheating and you generate this steam and you send it in the thermal power plant, you started with clean water, right. So, the water is clean, it is something that you had control on, and therefore, the steam that you get is also clean and that is used to run the turbines. Now, in the case of the geothermal plant, what is coming from underground may not necessarily be 100% steam. You may have some other gases in it, you may have even some radioactive material in it, etc. So, which may be coming out. So, therefore, what goes into the turbine, especially under these conditions when you are sending it directly into the turbine, is potentially something that can damage the turbine. Okay. So, therefore, you have to be cautious about it, and you have to take appropriate precautions with respect to the turbine materials to ensure that it is more corrosion resistant than maybe you would normally set it up to be. So, they put coatings on turbines, you can put different kinds of coatings on turbines just to ensure that there is greater resistance to corrosion, greater resistance to any abrasion, etc. So, that kind of precaution needs to be taken. So, but in any case, if it is superheated steam, it can be run to it can be sent to run a turbine, and also we will look at this, we can follow it up with a condenser that we will see in a moment. And basically we also need to if it is coming straight from the ground, if the superheated steam is coming straight from the ground, we do not want to exhaust that superheated steam. So, whatever happens at the end of the process, the water that is generated is put back into the ground at that location to ensure that the cycle stays operational. Okay. So, This is the general idea that people would like to do with respect to superheated steam. So, if you look at sort of a schematic, we will see a schematic here. So, we have somewhere further deep down we have hot spot. So, some hot spot is there where we have very high temperatures and you are able to get steam. So, normally what they would do is having found such a location, they actually drill 2 wells. So, one is called a production well, which is what you see here. So, this is the well from which they tap the steam. So, the steam comes up the way you see here and then goes into the turbine because it is already superheated steam. So, this is for superheated steam. Okay, so superheated steam, it enters, and this is just a schematic of some turbine that I have put here. So, let us say this is the turbine, and this turbine then rotates, you get this generator. So, this turbine goes and then the steam goes past the turbine, gets the turbine to rotate, and then the turbine is then connected to a generator here. So, the generator generates electricity and then you have an electricity out. Okay, so, this is the basic idea that we have. Now, after you cross the turbine, the steam would have cooled, or at least it would have completed its task, and then at that point we can send it back. This is what we say refer to as by saying that we should replenish the well. The point being that you have taken something out from under the ground, and if you exhaust it off, you may no longer be able to easily get the steam from that location. So, you send the condensed water back into the ground. So, this way you can keep it running indefinitely as long as there is heat down there. So, there is typically an injection well through which you complete the loop. So, you send this material back in, and that is called the injection well. So, now when you complete this, when you go past the turbine, right. So, the steam has then completed its work, it has done rotated the turbine, and you are about to exit the generator, I mean the turbine chamber. So, at that point you may still have it as steam. So, what should you do? I mean if you directly put steam back in here, it may not be as effective in terms of going back down into the injection well, and it may still have some energy. You have actually not fully captured the energy if you are just sending it back as steam. Just steam which was superheated significantly is now steam that is either just about saturated or just marginally superheated. So, you have not fully captured all the energy that is available in this process if you just do what is being demonstrated by the schematic. So, in fact, whenever they find superheated steam, they do one more step which happens in this region at the exit from the turbine area, where we say that we do not take what is coming at the exit, we do not directly send it into the injection well, we do one more step before we send it to the injection well, and that is what you will see here. So, what we do is we put in a condenser. So, what comes out is actually sent into a condenser. Okay. So, here it is allowed to cool down further till it becomes liquid water. Okay. So, it becomes liquid water and then it is sent into this injection well. Okay. So, this is what is done. So, this may not seem like much. So, you would say, so what? I mean you have anyway crossed the turbine, you have already crossed the turbine, what is the big deal in putting it into a condenser and then sending it into the injection well? There is a big difference. The moment you put it in a condenser, you have taken steam and made it water, liquid water. Okay. So, when you do this, the drop in volume is significant. So, steam is going to have significantly higher volume than the same amount of steam when it is converted into liquid water. So, there is a huge drop in volume when it goes from steam to water. So, now this drop in volume means what? So, you had, supposing you have a chamber, in that chamber you have steam. Okay. So, you have let us say some 1 meter cube chamber, 1 meter by 1 meter by 1 meter, 1 meter cube chamber that is filled with superheated steam. Now, suddenly you cool this and then this whole superheated steam suddenly condenses into some handful of let us say I will just give some example, maybe 100 ml of water is what it is, let us say, okay. So 100 ml or 200 ml of water, okay. So now suddenly there is a huge drop in volume, which means significant amount of vacuum is being generated inside that chamber, okay. So when you do this condensation, you are generating vacuum, because whatever was there, you have suddenly reduced the volume. The container still has the same volume, but the interior material that was inside that, the vapor that was inside that has suddenly condensed to a very small volume. So you have generated a significant drop in pressure, which is essentially you are creating a sort of vacuum. If you create a vacuum, then you pull the gases, pull the steam that is coming up here even much more effectively, okay. So and in that process you actually make the turbine work even better, okay. So by just the condensation process, by creating vacuum on the exit side, you make the whole turbine system work much better. So you actually get even more energy, you are able to extract even more energy out of the turbine, and as well as from the superheated steam that arrived at the turbine and through the turbine. So you end up creating much more energy or extracting much more energy. So therefore a condenser is actually a very important part that is that is added to this system of this geothermal energy process when you have a superheated steam, and it significantly helps improve the operation of that plant, and therefore this is always done, okay. So we never typically in this kind of a situation when you have superheated steam, we are not exhausting this we are not venting the steam out into the atmosphere. Instead we send it through send it back to the same location from which we took it out by using an injection well, and on top of it we also use a condenser to create liquid water, and then only then we inject it back into the well. So this is what you will typically see. Now this condenser may have some other may have a water some water involved in the condensing process. Cold water may be available locally, which is used for condensing process. So typically condensers you will see some vapors coming off of it, but that is from water that is other than what is being used for this that is coming through the steam coming from the steam, okay. So this is the kind of layout that is used if after prospecting you find a location where you have superheated steam. And of the possibilities that you can have when you do this prospecting, when you do this surveying for this geothermal energy, this is your best case scenario where you found steam and you were directly able to use it. So then the plant complexity is much simpler, and it is much more capable of extracting this heat for you. But this is not what you always find, okay. Often what you find is saturated steam. So saturated steam means it is just past the boiling point. I mean, so you boiled the water, is just past the boiling point, you created steam, but you are sitting at a temperature that is very close to the boiling point, and at that point if you do anything that cools the steam even marginally, you are going to get droplets of water, okay. So if you take even the tiniest bit of heat out of it, you are going to get droplets of water. So many places this is what is being found, relatively speaking, significantly more often, much more often than you find superheated steam, you are likely to find saturated steam. Now there is an issue with this. I mean, in some sense conceptually it is the same, you can still send the steam into a turbine and make it operate, and so in that sense you should not consider it dramatically different than using superheated steam, but we cannot use it directly because the condensation that happens creates droplets of water, and those droplets of water can damage the turbine over a progressive period of time. In all these cases, in all these technologies, many of these parts are expensive parts, and we do not want them damaged. Turbines are kind of expensive to make, and they are expected to last considerable number of years, so you do not want the turbines to be damaged. But when you have droplets of water physically going through the process, they can damage the turbines, they can lead to corrosion, many issues can arise. So what can we do? So the possibilities are different possibilities we can think of. We can actually try heating the water. So you have reached steam. So in a thermal power plant, you are basically taking water at say room temperature, and then using coal and heating it up to 100 degrees C, and then you heat it to get steam, then you heat it to get superheated steam, and then you send it into the turbine, right. So that much of energy you are getting from coal. Here you already have steam, okay. So it is just saturated steam, so it is already there in that you already taken it to 100 degrees C, got it past the boiling point, and it is in steam. So, with relatively less amount of coal, for example, if you had to use coal, with relatively less amount of coal, you can get it to become a superheated steam. So, that is a simple, so you you will not be 100% clean in that sense, because you are going to use some fuel, maybe coal, maybe oil, something to do this final bit of heating to get it to become superheated, and then you could use this, you can use the same turbine that you used before, etc. So, that is one possibility, but generally that is not done, because of course this whole idea is to run this in a very clean manner, and by including this burning of this coal, you are not really, you are sort of destroying that good aspect of this technology. And more than that, there is also the economic aspect of it. These plants are, as I said, they are not located just about anywhere. Some prospecting is done, and it is located at some maybe even in some remote location, which is where that hotspot happens to be. So, to run this plant, if you are going to adopt this strategy of heating it, then you have to keep transporting fuel to this remote location. So, and these are not small plants, these are typically you are trying to set up a plant which runs significant power capacity is there. So, corresponding to that, a significant amount of steam will have to be used, and therefore corresponding to that, a significant amount of fuel will be required. So, if you have a remote location and you have to keep transporting this on a regular basis, and these plants are set up to run for several decades, or if not more, then this is a big process you are setting up, which is not at all a convenient process. So, therefore, this is not taken into, this is typically not done. So, heating is not pursued in this context. The other option you have is that any time in any liquid, let us say you say just the way we spoke about melting point. I told you that if you have a melting point for a metal, you increase the pressure, you can go to even higher temperature, the metal will still not melt, it will stay in solid state, because you have put pressure to force those molecules to stay together, or atoms to stay together, and therefore it is unable to melt. And the idea of melting is they have drifted away from their crystal structure and they are moving around, but because of pressure now they are staying together. So, at high pressure the metal does not melt as easily as it melts at say 1 atmosphere pressure. The exact opposite would be true if you started going the other way around. If you start decreasing the pressure, then the melting point, the boiling point, etc., will actually decrease, because you have now made it easier for the molecules to separate out, right. So, therefore, if you manipulate the pressure instead of the temperature, you can create a situation where what comes as saturated steam suddenly has a boiling point that has decreased, and because its boiling point has decreased, it is now supersaturated, it is or superheated, it is superheated, right. So, this idea of superheating is relative to the boiling point, that is the point we have to remember, that it is relative to the boiling point. If you know what the boiling point is, if you heat the steam past the boiling point, say 10-20 degrees past the boiling point, then you have superheated the steam. But so you can do that by either, so you have T boiling point, so you have to go higher than this, so to superheat. So, we have to go to higher temperature to superheat it. So, now if you can do that by heating, if you do that by heating, the temperature of the steam is going up and therefore it becomes superheated steam. Alternately, you can do it by reducing the boiling point, or I would say lower the boiling point. So, if this is the T of the steam, if the steam temperature is at the boiling point at this under 1 atmosphere, if you drop the pressure below 1 atmosphere, the boiling point is decreasing, and therefore even at the same temperature. So, let us say this is supposed to be 100 degrees C, let us just say it is 100 degrees C. So, I will say that the temperature of the steam is the boiling point is equal to 100 degrees C. Let me just say that as an example. So, you can heat the temperature to let us say 120 degrees C, in which case the steam is superheated, or we can lower the boiling point to say 90 degrees C, right, 90 degrees C, let us just an example. So, if you drop it to 90 degrees C, if the boiling point drops to 90 degrees C, then with respect to 90 degrees C, 100 degrees C steam is superheated, right. So, there is only a relative term, and this boiling point is a variable. So, even though when we read in literature that the boiling point of something is a particular value, boiling point of water is 100 degrees C, we keep reading it that way and we think that is the only temperature at which water will boil. That is correct, that is the temperature at which water will boil under 1 atmosphere pressure. That 1 atmosphere pressure is something, it will be there in your textbook, but I do not think you would have paid attention to it. if you think about it carefully, you will find, go and look up this information, it will always say boiling point of something at this pressure, it will say that. We somehow do not, the pressure part of it does not register to us because we went only looking for the boiling point, and the pressure is always assumed to be 1 atmosphere because most of the time our operation is at 1 atmosphere. So, boiling point of water is 100 degrees C at 1 atmosphere. You drop the pressure significantly, you can decrease the boiling point. If you increase the pressure, you can increase the boiling point. So, this is so the boiling point is variable and depends on the pressure. And so, if you decrease the pressure, you can decrease the boiling point, and then the same the steam at the same temperature is now superheated relative to what its boiling point is. So, that is what is done, and this idea of lowering the boiling point by adjusting the pressure is called flashing. So, what happens is steam comes out before it enters the turbine, it will enter a chamber where it is allowed to expand. If it is allowed to expand, then its boiling point comes down, and therefore it becomes superheated. And once it becomes superheated, because the pressure has decreased, pressure has suddenly decreased, and therefore it becomes superheated, and at that point you can send it into the turbine. So, this is basically what we do. So, from the production well, the same process, you pull up the steam and you send it into this tank called the flash tank. So, here flashing is done, and this concept is called flashing, where you suddenly decrease the pressure, and because it is decreased, suddenly you have superheated steam, and then that superheated steam is sent into the turbine, and then that rotates the turbine, then you get the generator to operate, and then after that you can send it back into the injection well. And again, it depends, if you have if it is still it is still in steam condition, you can again put a condenser and again drop it to vacuum conditions, get the liquid water to form, and then you can send that liquid water down the injection well. So, this is the manner in which you would handle a situation where you have saturated steam coming into the becoming available to you coming from the location where you have done this prospecting. Okay, the third possibility is hot water. So, we saw superheated steam, we saw saturated steam, now we are looking at hot water. So, this is the third possibility that we have, which is hot water. This is actually found in many places. So, when you do the prospecting, this is what you are most likely to find. Most commonly you end up finding this hot water, in which case the process that is used, as I mentioned, is similar. So, we saw in the OTEC plant discussion that we had a couple of classes ago, that there you are only looking at a difference of about 25 degrees centigrade. You are looking at water coming from the bottom of the ocean, which is sitting at about 3, 4 or 5 degrees centigrade, and you are looking at water on the top surface of the ocean, which is sitting at about 25, 30 degrees centigrade. So, the difference in temperature is only about 25 degrees centigrade, maybe even less, 15 to 25 degrees centigrade is the difference that you are looking at. With that itself we are running a generator, right. So, with that itself we are running a generator. So, when you get hot water, when you do geothermal prospecting and get hot water, then clearly you can use the same concept, you can use the same concept that you are using in an OTEC plant. So, typically to do that you need to do something called a binary fluid cycle, and different again the idea is the same. If you have some vapor going through the turbine, you can get it to rotate, and so you look at liquids which have low boiling points. So, you can take butane, which is minus 1 degree centigrade boiling point, isobutane is minus 11.7 degrees centigrade boiling point, pentane which is 36.1 degrees C boiling point. So, you can use these as liquids as opposed to using water which is 100 degrees C boiling point. So, so to use water and then get steam from it and then run the turbine, you would have to be past 100 degrees centigrade temperature. But if you have got hot water, that hot water may be reasonably hot, it may be 80 degrees centigrade, 90 degrees centigrade or something like that, and therefore you may actually have considerable amount of heat available in it. It is just that it is not yet past the boiling point, it is not in steam. So, you use some other fluid and you exchange heat with this water, and using that process you run the turbine. So, for example, it would look something like this. Again you would have a production well. So, from this you pick up the hot water and it goes into a heat exchanger. So, this is very important. So, we have a heat exchanger that is out here. So, in this heat exchanger this water enters hot. So, you come here with hot water and what is coming out here is cold water. Okay, so, cold water is exiting from the condenser from the heat exchanger and goes down. So, there is another fluid which is running between. So, this is the fluid that is running from the well, from the production well to the injection well through the heat exchanger. So, your water does not see the turbine, it only sees the heat exchanger. It goes enters the heat exchanger, hands off heat and goes down cold. Then you take another fluid which could be any of these that we spoke about, butane, isobutane, pentane, etc. You find a fluid which is low boiling point and has the correct range of temperatures with which we can operate it in this situation, and that fluid enters here cold, picks up heat and then exits out here hot. Okay, so, it enters in cold, exits out hot vapor form, it will exit out. That hot gaseous form of that liquid of that pentane or butane or whatever you have taken fluid is now going to run the turbine. So, you complete running the turbine and then you exit, the fluid will exit out and it is now cold again and goes this way. Okay. So, you have two fluids here, the fluid that is coming from the underground and does this loop that we just saw, which is how the heat exchanger is picking up that heat and handing it off to the second fluid, which is the binary, and hence this is called this binary fluid cycle, because there are two fluids involved here. And the second fluid is what runs the generator, runs the turbine actually. So, the turbines are here and then that runs the generator and from here you get the electricity. Okay. So, this is the basic idea of this process where you could be running using hot water. Okay. So, and that is the way in which this system is set to run. Now, if you look at it as I said, the geothermal energy is available with differing levels of heat. So, we saw that based on the location you could actually have either supersaturated steam, superheated steam, you could have or you could have saturated steam, or you can have hot water. So, these are the three that you would get based on your prospecting. So, you do prospecting, and you could get one of these three, and therefore, this is varying from location to location, you get this, and then based on this you run a turbine with a condenser. You do flashing in this case, and in this case you use a binary fluid. Okay. So, so these are all the options that you have available to you, and in that process you can generate the electricity from the turbine, and therefore, the geothermal plant has to be designed to account for the differing prevalent conditions. So, whatever the condition is, as I said, you have three possibilities here which could be distinctly different in how their behavior is with respect to the turbine, and a lot of this, as I said, has got to do with in all these cases you are looking for efficiency, and you are also looking of life of turbine blades, turbine etc. So, life of turbine blades etc. That efficiency and life are the two criteria that you are using when you decide what is the design that you need to use. And I will also tell you that given that this is geothermal and you do not really have significant control on what is coming out from underground, significant variation is going to be there from site to site, both in terms of, I mean, this temperature is just one variation that we are talking of that decides, that is a very important parameter, because the design of this plant itself will be based on this variation of temperature that so clearly you have 3 totally different designs that have to be put in place. So you cannot just force fit one design to all locations of this plant. So this you have to do some initial design understanding of that location to decide what kind of a plant you have to use. But if you look at life of the turbine, you have to keep in mind that what comes out is not going to be pure steam, you are likely to have other things that are coming out. So your system should actually be capable of keeping track of that to ensure that whatever is coming out is not dealing with a turbine which is incapable of handling what is coming out, and therefore this turbine material is a fair amount of material science is there with respect to turbine blades, and lot of coatings are given, often ceramic coatings. So ceramic coatings are often given for turbine blades, primarily to ensure that the turbine blade does not directly get impacted by what is hitting it. Okay. So and that dramatically increases the life of the turbine blade. So sometimes zirconia based coatings are used, etc., and they are used to create this thermal barrier coatings, they are called, and that helps handle the temperature, plus also the fact that it is a ceramic kind of coating usually means it is much more resistant to attack from corrosion and so on, and so those coatings are very significant. Even if you can the actual blade, if it sees a temperature that is 5-10 degrees lower than the temperature of the gas that is hitting the turbine blade, then that itself would greatly increase the life of the turbine. On top of it, the if there are any particles that are coming by chance from underground, etc., which you do not have control on, the ceramic material will take the impact from those fine particulate material that may be present, and in that case that again helps protect the turbine blades. So the coating or the study of those coatings is a very significant activity, because not only do they have to understand which material to use, you have to also figure out what is the best way to apply that material on top of the blade, so that coating is uniform and has some predictable properties, so that you can safely say that for a certain range of operation of temperatures, certain range of compositions, the turbine blade will be safe. So even though we draw diagrams like this where you just put in a turbine system here, clearly since this is not a typical thermal power plant where you have a lot of control on what liquid is being used, I mean what is the quality of water that is being used, we cannot just like that put whatever is available in a typical thermal power plant cannot directly be used here. It is a good starting point, and that is probably where people will start, but you have to account for all these things. You have to account for what is available locally in terms of what is coming out from underground, and figure out if you need to put in additional coatings to make it run. So there are these conditions that we have to look at. People actively look at it, but as I said, the geothermal energy as an overall area of activity has all of those positives. The first thing is you are not depending on a particular find of oil of any nature. So in a sense it puts almost all nations on even footing. So many of the political aspects associated with energy are blunted when you look at energy of this nature. When you look at say solar energy, wind energy and geothermal energy, they get blunted. And if it is geothermal energy, to some degree, I mean clearly you do not even need access to the coast. So OTEC, for example, needs access to the coast. So even within the within a nation like India, only the coastal areas can immediately attempt to benefit from the OTEC kind of activity. Even there you have all this flowing water, and you have difficulty in controlling the pipes and the lifetime of the pipes, whereas here it is primarily a hole in the ground, and so to some degree it puts everybody on an even footing. You can actually do this at various places, although as I said based on prospecting they tend to pick specific locations in preference to other locations. Okay, so those are our conclusions for today's class. Geothermal energy is available with differing levels of heat at different locations, and plants have to be designed to account for the various different prevalent conditions prevalent, primarily looking at efficiency and lifetime of turbine, and with those aspects taken into account, this is a technology that is very clean and can be used at multiple locations. So, we will halt this discussion with this today, and we will pick it up in our next class. Thank you.